Hi everybody, welcome back. In this video, I'm going to do a bunch of conservation of energy problems. So just as, I guess, a preview before I do this, essentially what I'm going to do is use my conservation of energy equation, which is looks just like F equals ma is terribly deceiving, right? That's if no work, and if I do have work, I'm going to do it like this. Oops. Set up an equation that models this. Now, and then two things from this. First of all, this has signs, so you have to be careful. You add work when you're pushing something, and you take away work when you have friction. So those have signs. So if you have friction, you got to make that negative. This actually stands for total mechanical energy, which is the total kinetic plus the potential. And this can be expanded out to 1/2 mv squared plus the the potentials. Now you will not have every single form of potential. Maybe you will, that's just a long problem. But maybe you only have a stretch, or maybe you just have this. But you won't usually have both of these. Some people feel comforted by doing it like this. I'd like to have like this one giant equation to work with, which you can and reduce down. Some people like this because it forces you to analyze each one of these in your scenarios that you have, like that. I mean, technically, that's what this basically means. Isn't that fun? And like Inception of Inception, this one, oh, why didn't it change color? There we go. This one is work. So remember, work is force times distance. So it's not, sometimes they give you the work done, but if they don't, they better give you a force and a distance because you can't solve it without that. So, do I dare do it? Do I dare write this entire thing? I'm going to do it. I'm going to write the whole thing. I don't do this because of this exact thing. Look how long this is. Oh gosh, I'm already bored. Not even there. I'm not even at the end. This is not practical, folks. This is too long. Can you do that? Yes, you can. Because then what happens is if you don't have that energy, you say, oh, energy goes to 0, and that term drops out. But that's, like I said, way too much work. So I'm going to show you what you can do with all these questions. Oh yes, the inclined plane problem, right? This is like the bane of most of your existences. So imagine you have a skier at the top of the mountain. The skier is at rest on a frictionless incline. What's the speed at the bottom? So I just did it because I'm sorry, sometimes I'm automatic. But notice what I did, right? The speed at the bottom will have to be a final velocity. It's a velocity, but I put the final point there because it's conveniently what we need to know. How fast at the bottom? I put the end point there, not in the middle, because that's not where I need to find it. So that's my end point. My starting point I'm going to put up here because actually, besides the fact that the skier starts there, it actually gives us some information. The skier starts from rest, woohoo, which means my initial velocity is 0 up here. Super helpful. There's one piece of information. Second information is that it's frictionless, woohoo, which means there's no work. We don't have to worry about any sort of friction in this problem. So there's no non-conservative force. There's no stretching in this question, so there's no elastic energy. So the only other type of energy we have is height. Now this skier at the very beginning has a height of 185. Another reason why I want to pick this as my beginning point, because I have height here. I'm sure I literally can find the height in the middle because I have the angle here, but I don't want to do that. Why should I do that? And at the very bottom, notice it's very convenient to call this the height bottom because the height at the bottom is 0. And there we have it. So, essentially, you could do one of two things for this. The way I like to do it, well, I'll show you what I like to do, and then I'll show you the more systematic way to do it, and you can decide what you like. Notice that I only have height here and velocity here. So I could say that. I could say I have only potential energy in the beginning, and it all goes into the velocity at the bottom. This is a true statement. Or you can do this. You can say 1/2 mv initial squared plus mghi equals 1/2 mv final squared plus 1/2, mghf. And then notice it reduces down to this. The initial velocity is 0, so this whole term goes away. And the final height is 0, so the whole term goes away. Now, it might be best for you to do this approach because it forces you to think about things a little more. Once you kind of know how to think about things, then you could just make the equation kind of like I did. Now, the beauty of doing this is because the masses cancel. Notice that mass was not given. And that's always a sign that it has to cancel somewhere. Pro trick. This is a pro move. If you find something in your problem that's not there, it cancels out. Took me forever to figure it out. I'm giving you that tip for free. You're welcome. And watch what happens. So I get gi is equal to 1/2 v squared. And to solve for the bottom height, it's 2gh equals vf squared. And then I have to square root both sides, so 2ghi is equal to vf. And there you have it. How fast I go is only dependent on height, which makes sense, I think, for most of you if we don't consider friction. Higher I go, faster I go. Pretty simple. And of course G, although we don't usually go to other planets, so usually that's pretty constant for us. What's actually really cool about this result is the fact that the mass doesn't matter. Which means if we did not consider friction, and we're looking at a slide kind of face forward, and let's use, so here's my daughter, she's on the slide, you've all met her now because she's in all my videos, and then me. And assuming no friction, of course, friction would change the results. Not by too much, though. Fun fact. Now, we would get to the bottom of the slide. We go wee down at the bottom slide. We would both have the same velocity at the bottom. No way, right? We won't even have to hold hands. We would get there at the same time. Slide physics. Playground physics. There we go. Pretty crazy. Super silly. It only depends on the initial height, too. So, I guess we should solve this question since it asks so nicely. So, it would be the square root of 2 times 9.81 times the height. So, this is way easier than doing that whole, like, fxy, fxx, and all that fun stuff that you had to do to solve this. It was pretty crazy. 19. So I get 19.05 meters per second at the bottom, which is pretty fast. Just certainly faster than me on the ski slope, not gonna lie. I only went 11 meters per second. This person's going real fast. Didn't had any friction when they went down. But that's how you solve that one. There we go. This one. What is the speed at the bottom of the pendulum if it's released from rest from point A? So this is what I call your typical mean problem, because notice there's no mass in this, so that's not helpful. But remember, if you don't get mass, then it has to cancel. But notice another thing, they don't we know a little bit about a pendulum before I get to my point, right? We know that there's some height here, some potential energy at this point. But the kinetic energy at this point is 0 because it stops momentarily. And at the bottom we have all kinetic because it's moving. And we have no potential because technically I can put my 0 mark here, which is a very good thing to do. Quite honestly, it doesn't matter which one I called initial and final. It doesn't at all. That's just the way I did it. But notice that I'm calling this line my potential line. So I'm going to use a line because it's just nicer to use a straight line. Although I totally missed it. There we go. See if I can get it this time. Close enough. So I'm making this imaginary reference line where this is my 0 height. And you can do that. Fun fact. If there's an extra height, sure. But this is what the height that we care about is located. And if I draw like a dotted line right here, pretend that's in the middle. Just need it to be in the middle. Okay. So I don't even know if that's straight. But anyway, this line right here, that's where I'm measuring the change of height. Because that's what matters in the pendulum swing. Not how far it is above, but how far it was able to go to make that height. And lo and behold, they don't give you that either. What kind of problem is this, right? What's your problem? So I'm going to actually extend this line if I can. I don't know if I can do it perfectly. Oh, I can. Cool. That's going to be helpful. So hopefully it's straight like that. Alrighty. How do we solve this problem with nothing? Well, like I told you, everything I'm giving you are solvable problems. You just have to be, what's the word? Clever? Creative? Tricky? I don't know. So notice that we need h. I'm going to put h over here. We need this height. We're given the full length of this, right? And quite technically, from here to here, from the very top right here to here, this is also L, right? Because the pendulum doesn't actually switch its height. Its length at any one point. So what I could do is do a little trick here. Notice that this little piece makes a triangle. I'm going to outline it in red. Oh, you see my triangle that I made? What I can do is figure out x, which is this part. X is this part of the triangle, which I can solve because I have the hypotenuse and the angle. And if I know this and the L, which I do, I can solve for this. So let me show you my little expression. The length is going to equal to height plus x. Let's solve for x. X is next to my angle. This makes it a cosine. So what I can do is say cosine of my angle is equal to the hypotenuse, or the adjacent over hypotenuse, so x over L. But I want x, so essentially L times cosine of the angle equals x. So now I'm going to put x into here. L is equal to h plus my x, L cosine of the angle. I'm solving for h. So if I solve for h, I could take this whole term and subtract it over to the left side of the equation. L minus L cosine of the angle is equal to h. And there we have it in terms of L. If you want to get fancy, let's get fancy. We can extract that L out, and that becomes 1 minus cosine of the angle equals h. This is totally fine. You don't have to be fancy. But this is the height based on the length and the angle, if that's what's given to you. If they give you mass and height, then you don't need to do any of this, but it's good to see this method. So the same thing, all of the potential energy goes into the motion, or the energy like this. The masses cancel once again in this frame. And now I could do GHI is equal to 1/2 V squared. And then I can plug in H to here, so I get GL, 1 minus cosine of the angle, equals 1/2 V squared. The 2 comes up, so we get 2GL, 1 minus cosine of the angle, equals V squared, and then of course I could square root this whole thing. And there you have it. So now, basically, it's the same thing that I had before. So remember before, with just the ramp right here, it's actually identical, except we just redefined H as this part right here because we defined it in terms of the length of it and the angle. So like I said, if you have H, then this is super simple, and you can go this way. But let's be thorough and solve this question, right? So it would be 2 times L, which is 1.5. I have a great memory. Well, that's right, but let's do it in the order of this, which is 9.81 times L. And then I do 1 minus cosine, in this case it was 40 degrees, equals VF. And I'm just going to show you that I'm not making this up, that in fact it is 1.5 and 40. And then you can go ahead and calculate this. So I usually do the 1 minus that first, 1 minus cosine 40. I get a decimal times 1.5 times 9.81 times 2. And then I will square root that number, and I get 2.62. There you have that question. That was a fun one. Okay. So I'm not going to solve this entire question because it's just too long. I want to make a point about solving this question. So it wants us to, we are starting from point 1, and then we're going to each one of these locations, right? So when it comes to this question, notice that the two things that are involved are height and speed, just like before. Calculate the speed at all these locations. Once again, notice that no mass is here, which means they cancel. And remember, you get to choose your starting and ending point. So I'm going to be different to make a point here. Normally, I would honestly start from 1 and go to 2, 1 to 3, and 1 to 4, right? That's fine. Actually, kidding. I'm not going to do that. Okay. Let me think about this. Don't worry, I know how to solve this. I'm just trying to think of the best way to solve this to show you how to do it. I was going to do something else, but I don't think I want to do it that way. So what I think I'm going to do is this. Yeah, I'll solve the first two. 4, you can have fun with 4. Okay, so it wants the speed here and here, right? So let's start with the first one. So here's that thing that I'm telling you about, but making this the 0 point, right? Even though this is not officially 0, making this the 0 point makes your life easier because number 1, we actually don't have that point. And number 2, they gave us this, right? So we're starting at rest once again at VI is 0, which is super helpful. So we're looking for VF at the bottom here. So this is the same question as before. We say all of the, and then the height, if we call this the 0 point, then height 2, in fact, is 0 right here. So we could say all of the potential energy goes into the kinetic energy. This is for location 2. Masses cancel. I get 2gh is equal to vf squared, and then I do the square root of 2gh is equal to v. I did that way fast, I know. But notice it's just dependent on the height, so this becomes super easy to calculate. In fact, I'm being lazy, I'm just doing it like this with just the numbers. Pardon my laziness, I'm just trying to be fast. So I can get the speed at the bottom. So 26.20, this seems reasonable. Okay, cool. 3 is different. 3 is different. 3 is different because I do have a height here now. I'm sorry. I'll call this h. And I have a velocity. So the question's different here. And I can start from part 2 and go to part 3. That's totally fine. But I'm going to, like I said, this is actually easier. Going to 2 to 3 is actually easier than what I'm going to do, but I'm purposely doing it to make a point. So if I find the speed at location 3, this is how I'm going to start here again. Watch how I model this. So at the start, I have a height, which, I didn't mention over here, but we knew that, right? Height initial was 35, and I got that from this piece of information. From here to here is 35. So I have height here, but no speed, but I have both here. So for location 3, so I use a different color, do like a deep purple or something. For location 3, the way I model this is if I have all initial height, then I have both of these as my finals. So this is where it's a little different now, because now I have height here. It's different than here. This is 35 and this is 28. But it's there. Now the good news, masses still cancel. So I'm left with GHI equals 1/2 V final squared plus GHF. So if I want to solve for VF, I can move that whole term over. GHI minus GHF equals VF final. There we go. So what I can do, because we like to be fancy, is notice the G's are common. I could factor out that G and do G HI minus HF equals 1/2 V squared. And then the 2 can come up. 2GHI minus HF equals V squared. And then finally, 2GHI minus HF equals the final velocity once I square root it. That is our answer. Now, again, I can simplify this even more to show you something cool. Notice that this is basically a change of height, so delta H. So, in other words, if I want to find the potential, the speed of here, basically I have to know the difference in the height from here. It's like I'm calling this new location 0, if you think about it. That's essentially what I'm doing. 35 minus 28 is this small difference in height here. And that's essentially what's happening here. So in this one, it would look like that, right? So it looks like this. 2 times 9.81 minus the initial height and the final height. So 35 minus 28 gives you 7. So the final velocity, after I just plugged them all into my calculator here, and there you have it. So notice that it's slower than what you had at the bottom. Hopefully that makes sense. If you think about a roller coaster, right? As you go down here, you get your fastest down here, then you come up the hill, then you don't stop, but you definitely slow down, and then you get faster again, etc. So that's essentially how you would set up something like this. So you have multiple ways to solve for, which I'll let you do on your own. In fact, I'll even let you do it on the homework, because I think I have this question on the homework. I did that on purpose. You know, just trying to be consistent. And not every homework problem should be super foreign to you, but, you know, enough that you have some experience with some common ones. But anyway, the point is it looks different because now we have both terms here. Where are we? Okay. So for this question, I chose this question because now we have elastic potential energy to deal with because we haven't done one of those. So that's why I'm going to do this one for you. All right, let's take a look at this. We have the trampoliner artist jumps vertically upward from the platform with a speed of 5 meters per second. So he jumps upward vertically with 5 meters per second. Like that. How fast is he going as he lands on the trampoline? So about, here, what's the VF? And then, if it behaves like a spring, how far below does it go? If it stretches, right? So we're looking for X. I'll make X a different color because that would be a different question to the problem. Something that we can see maybe a little better. X, like that. I totally exaggerated this X, by the way. It's not going to depress that much. It's going to be a teeny tiny amount. But I purposely did it so you can kind of imagine what's going to happen. So here we go. So once again, we get to choose our start and initial point. So if you remember from objects thrown upward, this person even will start with 5 meters per second. And if it comes back, this person comes up, right, and comes back down at the same spot. The magnitude of this velocity is still the same, but negative. So in other words, the initial velocity, I could start as 5. I could start as 5, but technically right here. He's moving at 5 meters per second at that point. And we want to know how fast he's going at this point. But this person also has some height, right? So right from roughly, I missed the mark, but that's okay, you get the idea. From here to here, the initial height is 3 meters. So watch the way I model this. Now we're not stretching it yet, so we're not there yet. So notice I didn't do anything with the stretching. So in the beginning, I have gravitational potential energy plus speed, so kinetic energy, is going to equal to the final kinetic energy. I don't know why I wrote that backwards. So that's how I model it. Notice how I'm making the equation each time, right? I look at what's happening in the system, identify the initials and finals, what kind of energy is there, and work from there. And just to be, right at this location, the height is 0. And notice that there's no term here. Masses do cancel here. And then I can go ahead and solve for the final. So GHI plus 1/2 VI squared equals 1/2 VF squared. I can multiply 2 on both sides to get rid of that half, so it looks like this. And bonus points, did you notice this looks exactly like a kinematic equation that we know already? Ta-da! Isn't that crazy? It models the same thing. Except instead of X, we have H here. But it's the same model because it's the same kind of understanding and idea. So we could use kinematics if we wanted to, or we could use energy. When it comes to your final, you can use either. It doesn't matter. Let's plug in our numbers. So it's going to be the square root, because this is squared, of 2 times 9.81 meters per second squared, times the initial height, which is 3 meters, plus the initial velocity, which is 5 meters per second. Now, if you make that negative, it's fine, because the negative will go away with this, and that's the final V. Let's go ahead and solve that out. 2 times 9.81 times 3 plus 5 squared. I didn't have to do that on the calculator, but I did. And then I had 9.16 meters per second. So Looks good, he's got faster. That's good to know. So that's the velocity right here. That's all there is to it. Part B. How much does this compress? So this is fun because you have options on how to solve this. You can start where I ended and solve it here, or you can start up here and skip all that part and go right to here, because we're looking at the energy transfer of this. So I'm going to start here. For part B, I'm going to start from where I ended. So start here. That's because I already have that number. And of course end here. Now, like I said, I super de-duper, like that one, exaggerated this length. So in other words, the height's not going to be a role in this. What's going to happen is all of the energy going into this motion is going to go to stretching this object. So there's really not a substantial potential energy in this part. So I'm going to ignore that, which I know looks like we can't. But all of the initial energy is going to go into stretching this spring, which we're treating like a spring. Notice that this doesn't cancel the mass, which is why we're given it. So that's very important. What can cancel is the 1/2. That's kind of nice. mvi squared equals kxf squared, where k is our spring constant. So mvi squared over k equals x final squared, the square root of all this, equals x final. The square root of 65 kilograms. Sorry, that's an unclear 65. Times the initial velocity, which is the final velocity from before. Now, the k constant is this large number right here, so it's a pretty hard to move spring, which makes sense. And there we go, 65 times 9.16 divided by 62,000, square root the answer. Perfect. 0.098 meters. So this is the official answer. That's what you would type in, but just for perspective, this is 9.8 centimeters. So like I said, even if we did calculate the energy associated with the potential, it'd be teeny tiny. It'd be negligent. Negligible, not negligent, sorry. I get tired at night. Negligible. And negligible means that it's a quantity that's not going to affect the answer that much. So that would be our x in this case. So here is it with, so a big major issue with this is you cannot cancel out the mass here. Some people do this by accident, and you can't cancel k out with m. I know it sounds really obvious and silly, but when you're working and you're tired and things are going on, sometimes you make these silly mistakes. So that's a silly mistake that people make with that. So just bear that in mind. Okay. Okay. So now let's work with something that does have a non-conservative force in this system. So even though I've written it like this, I'm not going to use this form, but that's okay. You'll see it as we go along here. All right, so suppose you push a block with initial velocity of that. How far does the block move? Like that. So typically we've used forces to this, but now we're going to use energy. So let's see. We start off with our block, and we have an initial velocity of 3 meters per second. Okay. How far does the block move? So from here to here, I don't know if this red is either blinding or what. Maybe I'll do a different color. Less blinding, yes. So it doesn't say otherwise, but we can assume that the block will come to rest. It makes sense, hopefully. It doesn't get faster. It's going to slow down. It wants to know how far the block has moved, so some distance d, like this. Notice that there's no height here, right? There's no height change. It's on a level place. It doesn't say we're on a ramp or anything, so there's no height here. There's no stretch. So there's no potential energy. In fact, the only forms of energy are kinetic and work done by friction, right? Because friction, if I were to draw this on here as a free body diagram, that won't work. So friction, we have force gravity, force normal, and then friction, right? So usually you don't draw the motion of the object on a free body diagram, but it's okay. We're not really modeling the, notice it's a different color, so we'll go with that. So what I'm going to say here is that all of my kinetic energy goes into the work done by friction. Which doesn't seem like a conservation of energy problem, because we kind of did this already when we did work energy theorem, but it's totally related. So what we have here, in fact, is more accurately, we have to do it as the change, right? So, so kinetic energy final and as such, so 1/2 mv final squared. Hold on. This is fine, everybody. But I want to do it, this is fine, by the way. This is totally fine. I'm going to just show you the way I have it written before. Because if you notice, I actually had conservation of energy written as this. So I'm going to do it this way on purpose. And you'll notice that this will work out anyway. So this is, I got this from the, in like a couple slides ago. I've written out the entire thing of, let me show you where I'm getting this from. This, okay? So no elastic, no potential. No elastic, no potential. So I rewrote it in that way. So I'm going to do it that way. Okay. So with that said, work is done by friction, so this will be 1/2 mv initial squared plus force friction times d equals this, like that. Now, remember, friction is going to be a negative force because it's going to take away energy. So what I'm going to do with that then is put a negative sign here. And that's because we're taking energy away. So that's why I added that piece in. So this is what it looks like, right? So the final velocity is 0. Cool. Because the final velocity is 0. Like I said, you get the same result if you did it the other way too, just fun fact. And I forgot the d in here. There's a d. Force friction times d. Now notice this is negative, so I moved it over. So we have this. Now force friction on a level surface, so we have to go back. So force friction is force normal times mu. If you're a level surface, then force normal is just mg, it's just the weight of the object because they're equaled out. So if you look up here, these two forces are equal. So I get 1/2 mvi squared equals mg ud, where m's cancel. I'm looking for d. So d is going to be v squared over 2g mu. And that is my d. So that's the conservation of energy perspective of solving this. So how fast was it going? 3? 3. 3 meters per second squared. 2 g. And mu was what, 0.45? By the way, we definitely have solved this using the work energy theorem. So yes, you could do it multiple ways. Doesn't matter which way you choose. I just like to give you options of your choosing. This goes 1.02 meters. Let me double check that. I think that's right. 3 squared is 9 divided by 2 times 9.81 times 0.45. Yes. Okay. It doesn't go far. I was a little disappointed with that number. But you don't push it very fast. It doesn't go very far. It makes sense. Okay. So that's one way you can look at this. Yes, so we kind of looked at this before, but yeah, so how would you model this? All of the kinetic energy goes into the work done by friction, which means your final energy of the system is 0 because all the energy is taken away from your system and gone into the environment. Yes, so we talked about this. Very good. Okay? Okay, perfect. All right. The skier starts from rest and slides down the incline. If the coefficient of friction is that, what's the skier's speed at the base of the incline? If the snow is level at the bottom, how far will he go? Okay. Okay, so you can do it in 2 parts, like the way it has it, or you can do it as one big thing. If for part B, like I said, you have lots of options. But we have to be careful now because we have our non-conservative force of friction. So how far this moves does matter and affects our answer. So let's analyze it. So at the beginning, we're at rest. It says this is 22 degrees. It says the incline is 75 meters long, so that is this number, fun fact, not the height of this. So that's 75. And there's friction on this. So yes, because it says coefficient of friction, so there's definitely friction on this. What's the skier's velocity at the bottom? We have some height here, but we don't know what that is. But we are clever physicists, and we have the hypotenuse and the angle, so we can find h. That's not a problem. But we do have h here, so that's important to note. So watch what I'm going to do. We have gravitational potential energy in the beginning. We have no kinetic, we have no stretch. But we have work done by friction. And that's going to go into the energy at the bottom, which is all kinetic. So we're recognizing that this, in fact, is 0 right here. So I'm adding in the work, but I am definitely making this negative because this is work done by friction. So I'm going to rewrite this statement as mghi plus force friction times mu, times d is equal to 1/2 mv final squared. Almost simple, except that the force of friction is based on the normal force, and this is not level. Force for normal here is not going to be this for inclines. Which means we got to figure that out. So, side note, we have to do our nice little free body diagram. So we have gravity down, we have normal to the side, and we have friction like this. And that's for the incline. So if I were to rotate this coordinate system so that I have this situation, I love that I have lines. Having lines is incredible. redraw my coordinate. I always do this, even though it's a little tedious, but I think it's just much more clear and easier to think about it this way. So I have force friction, sorry, force normal, which is directly up. So that's drawn right here. I have my gravitation this way. Angle here is the same as the angle of the incline, and I have force friction this way. So what I find here is this component of the force of gravity, so Fgy, has to equal to the force normal, because there's no vertical motion. Which means that this is a cosine because this is next to it. So Fgy is going to be Fg cosine the angle. And Fg is mg. So mg cosine of the angle is equal to the force normal of this case. So mg hi plus mg cosine of the angle mu d, that whole thing is force friction because force friction is force normal times mu, equals 1/2 mv final squared. Now we need this piece here, which is basically a sine component. So we can write this all in the fun way of doing this. This becomes mg times, I'll call this the length L, L sine of the angle. So that is basically here, where this is L is the length. I don't know why I'm in a very big solve it with a what should we call it, symbol mood, as you can see. But I think there's definitely value in solving it this way. You can plug all your numbers in at any point, please know that. In fact, you could start here and plugging in numbers, that's fine. But one of the nice things is you do get the cancellation of m, which once again you see that mass is not given. So you can cancel it. So that's why writing it this way is helpful. But we do have everything else. So what I'm going to do now, even though this is super tedious, I'm going to write it down here again, just because I want to be able to solve it. It's minus, right? I'm pretty sure it's minus. It's minus. Oh boy, see? Minus, I was right. Mg cosine of the angle mu. People forget mu all the time, so just be careful with that, including myself. When I say people, I kind of mean me. But people make the same mistakes. So yes, these all cancel. G L sine of the angle minus G cosine theta mu d is equal to 1/2 VF squared. Remember, you can be fancy sometimes. You can factor out the G and the 2 comes up, so we get 2G L sine of the angle minus cosine of the angle mu d is equal to V squared. The square root of all this, we'll get a circle velocity at the bottom. So you can see it's a little more hefty. Once we get into the mode of, adding friction, it actually makes it substantially harder. So let's go ahead and do this. L is 75, sine of 22, cosine 22. Mu was 0.01, I think, and I'll double check that. Now D is the same thing. It went 75 meters. So I could have Sloppy. If I made this the same variable, I could have pulled that out too. It's okay. I'll let it go. No, I won't. So technically I could have written it like this. 2GL sine of the angle minus cosine of the angle mu equals b. Sorry, I would not be able to sleep if I didn't write that. Okay. Okay, so this is funsies, right? So I'm going to start from the middle. Cosine 22 times 0.01. Let me just double check that coefficient of friction. I don't want to do this whole thing and then find out that it's wrong. 0.09. See? See? I told you. Probably were yelling at me. It's no 9. 0.09 times 75. 75 times sine 22 minus my previous answer, so 6.258 times 9.81 times 2. Screwed with the answer. Perfect. Memorize the answers. So 20.69 meters per second. Wonderful. Ta-da! There you have it. It's just longer, right? It's just like, oh, what did you make me do? It was so long. So yeah, it's part A. If the snow is level at the incline and has the same coefficient of friction, how far will it travel? Use energy methods. Okay. So what you can do for the next part is basically they're talking about that part from here to here. I'll call this X, just to be different from L and H. So, if you use the similar energy methods that I used earlier, you can do it just like this. Where this is now the initial. But now, since we're on a level surface, friction is a little easier. There's still friction, you can't ignore it. And that force normal in this case is the weight, is mg, so thank goodness, right? So we have the initial velocity, so we'll have kinetic energy, minus the work done by friction, or I'm going to call this delta x because that's the distance, equals to the final kinetic energy. There's no height change, there's no potential here, that's 0. This is what we did earlier. I'm going to purposely do this so that you can see that when I write it like this, we have force friction times delta x. Force friction is force normal times mu, which will be mg mu. M's cancel, which is important. What do we want to know? Distance. Okay, so yeah, it's the same result as we got before. As such. Now, don't let me do all your work for you. In other words, if you, when you're doing your homework or your exam, it is nice and easy to be like, oh, it's this question, it's this equation. It can work, but you have to be careful because maybe it's not mg mu, maybe it's the cosine piece or whatever the situation is. So you just have to be extra careful that you don't memorize this, that you understand how we got to this point. I did the work for you, but you have to think through it too. Because it's not about here's the equation and plug it in. It's not. If that were the case, then I would just give you the equations in the beginning of the semester of every possible scenario. You would cry because you would say there's just hundreds of examples and how am I going to memorize these all? And then I say, well then that's the point of the course, to memorize them all. So tough? Well, I don't know what I would say, to be quite honest. The point is, make sure you understand how I get these and not just plug and chug, okay? I can't see your faces or reactions to any of this. I don't know what's happening. It goes pretty far. It doesn't have a lot of coefficient of friction, so I think it's going to glide forever, which seems like it's a far distance. But that's our delta x right there. So yeah, things get more complicated when you add friction. True story. Okay. There you have it. So I'm going to spend the last part of this briefly just talking about the graphing of this. If you're taking Physics 110 as a lab course, you would actually do this as a lab where you would actually make these exact, very similar graphs that you're seeing right here. You're also reading, if you're doing it online, you're going to be doing reading of graphs on maybe PhET, for example. So I'd like to go over this really briefly. So it's really important that you can read these graphs and understand what they mean. So, for example, this is the energy versus height of a falling object, right? So notice that as you, how should I, let's say it this way. So notice the height here, right? So as you might imagine, the more height you have, the more energy you have, and this is a linear relationship. MGH is a linear relationship with height. So you could see that relationship when we graph it. But here's a different type of graph. Here's the potential energy of a spring. So what happens is the energy of the spring, which is 1/2 kx squared, notice that x squared makes this a nonlinear function. In fact, it's equal on both sides because the spring can stretch and compress. Pretty cool, right? So usually what you'll do is you'll read graphs and you'll see that there's this horizontal line there which represents the total energy of your system. Then we have these things called turning points, which are exactly what they sound like. The spring stretches, stops, comes back, right? Stretches, stops, comes back. That's a turning point. In fact, that's what happens when you have the maximum kinetic and elastic energy. You also can figure out your kinetic energy because this is the curve of the potential. So you would read it as, as following. As you go up to this exact location, you have 4 units of potential energy. And if my total energy is 11, well, 11 minus 4 gives me my kinetic. So you can actually read and get information about the kinetic energy based on where the potential is. So the maximum force, the max or the min, not force, the maximum or min, so if this is very calculus based, so if I were to find the minimum point, it would be right here. In other words, where the slope is 0. That's when you don't have any force. So if you think about it, if you don't stretch the spring, you have no energy and no force. So that we call this stable equilibrium at that location. Yeah, I kind of went over this already. I like this one because it's a slightly different kind of perspective on this, where it looks at the time. So the time is not linear if you think about it, because what happens is that essentially you have the 1/2 mv squared portion of it, but the displacement, if you notice, is squared. So instead of getting that straight line you did before when it came down to the falling with the height, the falling with the time gives you a curved line. And in fact, you should definitely try this on the energy skate park. You can actually get the energy versus time graph, and you would see this. Another really interesting and cool thing about this is the fact that as the potential energy decreases, the kinetic energy increases. And vice versa. As these go back and forth, you would see it like this. So that's another really interesting feature about this. So here's a quick question about this. So if you take a look here, at x equals 4, what's the speed, and then what's the turning point? So if you remember, this is the total energy right here, this dotted line. So 150, which they kind of pointed out, which is fabulous. So if I read this graph at 4, and of course you're reading this as best as you can, it just happens to fall in a nice location, which is 50 joules right here. 50 joules, as I'm reading it, is the potential energy. So know that that's the potential energy. I'm reading the curve. So if I want to get the kinetic energy, which is this part, we're going to take the total energy, E, is equal to the potential plus the kinetic. We know that the total is 150. So I need to find, by the way, I didn't tell you why I'm doing this, because kinetic is going to give me the speed, because that's how I get the speed through kinetic energy. So 150 joules is equal to the, there it is, 50 joules plus Ke. And if I subtract both sides, Ke is 100 joules. My speed is going to be 100 joules is equal to 1/2. 4 kilogram mass, sorry, it's up there, times v squared. So what I'm doing, again, I'm moving too fast, I'm sorry, is I'm setting this equal to 1/2 mv squared. So 100 times 2 divided by 4, square root my answer. The velocity at that instance is 7.07 meters per second, like that. So there you go. I can find how fast it's going without even recording the speed at any one point. Nifty. What's a turning point? Turning points happen when you have the max energy, or point right here. So probably around a little over 7. So if you said like 7.25 meters, that's fine. Anywhere near 7-ish would be acceptable, like that. So I'm reading the graph. In fact, let me just look at where it actually is. I think I just drew it really terribly. That's about right here, yeah. Right there. Yeah, it's a little, you know, that's the turning point. So it's at where the PE and E cross, basically. And look at x-axis. So it's about 7 meters, give or take. When you read graphs, as long as they're close to the values that seem reasonable, I give you full credit, because clearly you're reading the graph, so it can be slightly off when you read graphs. Yeah. So just to show you, I'm not going to go over this because I'm not a chemist, but I will just tell you that you actually see these kind of across the curriculum. So this is a potential energy graph right here, and this is all about the bonding forces and stabilities of atoms. So there's a sweet spot where atoms like to be in terms of their distance, right? So they kind of get stuck here if they have too much distance. So as we get further, this is distance, right? As you get further in distance, they become weaker and no longer want to stay together. And then if they're too close, then you got the repulsive force. So in other words, they're two hydrogen atoms of the same sign. They're not going to want to stay next to each other. Although there's some other things going on there, which if I do part 2 of this course, you would learn all about. But anyway, you're not required to read this. Don't worry, you don't have to understand this. I'm just telling you that potential energy graphs exist in all different courses, including your chemistry course. So, in conclusion, is if there's no outside force, the system will remain constant in its energy. If it has work done in the system, or in other words, non-conservative force, if you push an object, you're going to add a force and motion to the system, and if you have friction, you're going to take away motion from the system. Non-conservative forces are forms of work, so it's just a physics word for that. I like to just say added work and take away work. Textbooks like to talk about conservative and non-conservative forces. It doesn't matter how you call it, as long as you understand the process. And then, of course, how to read the energy graphs. So you'll look at some of those on your online homework with that. So as always, if you have any questions with any of these, just let me know. Have a great evening.